So these are the final exam review slides for Organic 1 in the spring 2016. So figure we go through these quickly to help you guys study with that. So one of these questions is going to be hybridization. Remember, right? So these are typically going to be SP, SP2, SP3, right? And so what you want to do is you're looking for bond sets, right? Plus lone pairs. Okay, lone pair sets. Okay, that'll tell you how many letters. Once you add those up, that's going to tell you how many letters are going to be in the you need for your in your hybridization, right? So with that, so this one here, right? So here's one bond set, right? Here's another bond set, right? So with that, so there's two, right? So no lone pairs on that carbon, right? So 0, right? So 2. Okay, so that means we need 2 letters, so it'll be just to be an SP. It'll be an SP orbital, right? So start with the S, and then keep adding P's until you get to the right number of letters. Okay, so for this one here, right? So there's 2 bond sets for that oxygen, right? And there's 2 sets of lone pairs, right? So 2, right? So 4, that means it's S, P, 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 right? 4 letters, 1, 2, 3, 4. So it's SP3. Okay. Now, if I were to do, say, this carbon there, okay, right? So with that, so don't forget that there are 3 hydrogens on here. Okay, I don't have to draw this because it's a skeletal structure. Okay, so with that, so that means that there's 1, 2, 3, 4 bond sets, no lone pairs, 4, which makes it SPPP, right? SP3. Okay, so don't forget on the skeletal structure, I don't have to draw the hydrogens. Okay. Now, formal charge, right? So with that, so what you're looking for is number of valence electrons minus the number of electrons now. Okay, so oxygen typically has 6, right? Now we're going to subtract how many it has now, right? So to do that, right, each bond has 2 electrons, right? Right, so this bond there, right there. You're going to slice those in half. So now the oxygen is going to have 1, 2, 3, and then this set of lone pairs, right? So now it's got 1, 2, 3, 4, 5, right? 5. Which makes this formal charge +1. Okay. Okay, for this one here, for the resonance structures, right? So what do you need to be able to participate in the resonance structure? You need either part of a double bond, right? Double, triple bond, right? Triple bond will work too. Right? Needs to have a lone pair, or it needs a charge. Okay, if it has any of these 3 things, then it can participate. So this one here has a charge. These 4 carbons here are part of a double bond, but this carbon here, right? It only has single bonds, no lone pairs, no charge. So we can't deal with that carbon there. Okay, all the rest of the carbons can participate. So I'm going to go ahead and draw in all these hydrogens. Okay. Okay, so you usually want to start with the charge here, right? So with that, so this carbon, right, has 3 bonds. It wants a 4th. So the easiest way to do that is to shift this guy there. Okay, you're going to be shifting those pi electrons over. Right, so it looks like this. Now you don't obviously have to draw the hydrogens. It's just sometimes easier to see what's going on if you go ahead and draw them all in. Okay, so we've moved these pi electrons up there, so now this carbon here only has 3 bonds, so that gets the positive charge. Okay. Now we can also move, right, to get that 4th bond on this carbon, we can shift that guy over. Okay, so now that's there. That's there. Now this carbon only has 3 bonds, so the charge is there. Okay, so with that, so if you notice, right, so on these structures, it went here, skipped there it went there, skipped, and then went there. Now we can't go forward around the ring, right, because this carbon here can't participate. We're at the end of the line, so that's where we stop. Okay. So there we go. So it's all about making typically carbon carbon have its 4 bonds, stuff like that. So. Okay, so naming the alkane, right? So with that, so when in doubt, go ahead and draw in your dots for your carbons. Okay, so you're gonna want to know the longest chain, right? So don't forget to go down those side chains too. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, 7, 8, right? So with that, so this guy here is going to be our main chain. Just so happens that it happens to be the horizontal. Okay, so C9 equals nonane. Okay, so that means we have a methyl group right here, ethyl group here, and another methyl group there. Okay, so good practice. Go ahead, do the numbering. Right, so going from left here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so 3, 4, 5. Right. If we went from this side, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So in this case, right, so it'd be 5, 6, 7. Right. So you add these up. So this would be 12. Okay, this would be 12. This would be 18. Right. So you're gonna pick the lower numbers. So there we go. Okay. Now, the right. So which gets labeled first? We have methyl, ethyl, another methyl. Right. So the ethyl gets labeled first because ethyl comes before methyl. So it's going to be 4 ethyl. Right. 3, 5 dimethyl, and then put the main chain at the end. Okay. So what do we have? Right. So we have a main chain that's 9 long. Right. Main chain that's 9 long. Right. We have 2 methyl groups. Right. Right. So one at 3, one at 5. Okay. We also have an ethyl group. Where is it coming off of? It's coming off of carbon 4. So there we go. You can always do your double check. Okay, so for acid-base reactions, right? So, right. So for here, right. So this acids give H plus, right? Bases take H plus. Okay. You can always think about, right. So the reaction of HCl, right? You know, this is your acid, right? So this is hydrochloric acid, right? Plus, you know, base, sodium hydroxide, right? Okay, so this is your base. What does it do, right? It's taking the hydrogen, right, to make salt and water, right? So you can always think of water as HOH, right? Same thing's happening in the organic chemistry world. Okay, we have an acidic hydrogen, which usually ends up being off of a heteroatom here, right? That's going to come and take that, push those up, so you're going to end up with this, right? This pair of electrons is going to make a bond with that hydrogen, right? This one the hydrogen only needs 1 bond, so these 2 electrons get pushed up, so you end up making a third set of electrons here, which gives oxygen this oxygen a negative formal charge, right, plus HOH, right? So those are your products. So I'll tell you which one's acting like the acid, which one's acting like the base, right? But they all work exactly the same way. The base is going to come in, grab a hydrogen, rip it away, right, to leave you this. Functional groups. Okay. Now, typically what you're looking for, right? So you don't have to find the alkanes, cycloalkanes, benzenes, right? If you can't find those, then we've got bigger issues, right? So what are you looking for? You're looking for basically heteroatoms, non-carbons, right? And double bonds. Those are really the big things that aren't part of benzenes. Okay, so you usually just start at one end and work your way around, right? So this guy here. Right, the C double bond O, that's a classic thing, but you have to see what's on either side, right? So we got a carbon on one side, carbon on the other. That makes this a ketone. Okay, right, so we have two double bonds here, right? So with that, they aren't part of a benzene, Right? I know they're part of a 6-membered ring, but remember benzene goes double, single, double, single, double, single, double, single, and round. Okay, this one is just 2 alkenes. Alkene, alkene. Okay. Now these fluorines here, right? So you can call them halides, right? Fluorines, that's fine. Right. So there and there, that's fine. Okay. An OH all by itself, right? So it's just on a just regular carbon, right? This is an alcohol. Alcohol. Okay. Looks like that's pretty much it. This is just a CH3, right? So that's nothing. Hydrogen's doing. Worry about that. Okay. Now this one here, right? So with that, so here we have, right? So C double bond O, right? But an OC on one side, right, and just a regular carbon on the other, right? So if it's an OH, it'd be a carboxylic acid, but the O carbon makes this an ester. Okay. This one here, right, so C double bond O, right, carbon on one side, that's good. But a sulfur carbon on the other, right? So with that, so this is the sulfur version of an ester. So this is called a thioester. Okay. And then lastly, this guy here, which would again be a halide or a fluoride or fluorine or whatever it is you want to call it. I don't know what you're talking about. There you go. So you get 1 point. So this is Flovent, by the way, used to treat asthma. Right. So it's a steroid, right? Because he has these 4 fused rings, 3 6-carbon rings, and a 5-membered ring. So with that, so in this position, so. Okay. Now, for these guys here, okay. So here you go, right? So put in your dots. Okay. Now, you're either going to be part of a straight chain or you're going to be part of the ring. You can't be both, right? So you're either talking about these 3 carbons here, 1, 2, 3, as part of the straight chain. Or you're talking about these 6, 1, 2, 3, 4, 5, 6. You don't go in and around like that. Okay, it's either part of a ring, part of a straight chain, and that's it. Okay, so the main chain in this case, right, is these 6. Okay, so C6, right? So that would be normally be hexane, right? But to say hey, it's a ring, it's cyclohexane. Okay. Now we've got these 3 chains, these 3 side chains here, right? So we have the methyl. We're going to treat these methyls independently. Okay, so methyl. Okay, and then this guy here is a propyl. Okay, so we're going to figure out if this carbon is number 1 or this carbon is number 1. We don't know which. Okay, so this is what we'll do, right? So we'll take, say this is number 1, right? We go either clockwise or counterclockwise towards nearest side chain neighbor. So here we go. So here it's right there. So it's 1, 2, 3, 4, 5, 6, right? So these would be 1, 1, 2, like that. Now if we said this was number 1, okay, the nearest side chain neighbor is here, so that would be 2, 3, 4, 5, 6, right? So this would be 1, and that would make both of these 2. So we add them up. Right, so this is 4, this is 5, right? So it becomes 1, 1, right? So and methyl comes before propyl, so it becomes 1, 1 dimethyl, 2 propyl, cyclohexane. Oops. There you go. Okay. Now for this one here, right? So you can always put in your dots, right? So we got a 3-carbon side chain here, 1 carbon side chain here, but we have a 5-membered ring here, so we're going to make that our main chain. So C5, right? So it would be pentane, becomes cyclopentane. Okay. Okay, so that means we've got this group, and this group. Okay, so we have 2 methyls, right? Methyl, methyl. Okay. Now this group, which would be a propyl, okay, because it has 1, 2, 3 carbons on it, but because it's connecting to the main chain through carbon 2 of the propyl, we call that a 2-propyl group. You can also call it an isopropyl group. Okay. So let's do the numbering, right? We're going to say if this is number 1, this is number 1, or this is number 1, right? So here we go. So we have 1, 2, 3, 4, 5, right? So that would make this 1, this 3, that 4. Okay. Now if we're going to do this number 1, right? You go clockwise or counterclockwise, right? They're equidistant, so it doesn't really matter. So this one here, right? The nearest side chain neighbor is here, right? So it's 1, 2, 3, 4, 5, right? So that makes this one 1. Oh, I think it's this one 1, this one 2, this one 4, right? Now if we did numbering here, right? So nearest side chain neighbor is over here, so 2, 3, 4, 5, right? So here we go 1, 2, 4. Okay, so we're going to add these up. So, right, it's 8, 7, right? 7. Okay. Okay, so we know it's not this. And then, so what we would do if there was a tie, right? We say, oh well, that it goes. The number 1 goes to the one that's the first alphabetically, but it doesn't really matter if it's a methyl, right? So it actually would give you the exact same names. So this one ends up being 1, 2 dimethyl, right? Because methyl comes before propyl, dimethyl, methyl. 4, 2 propyl. Cyclopentane. Okay, there you go. Okay, now, are the compounds cis or trans? Okay, so now for this one here, right, so cis is either going to be, right, that means the same. So they're either going to be up, up, or down, down. Right, trans meaning up, different. One's going to be up, one's going to be down. Okay, so for these guys here, okay, notice how they're both going up, up, up. Okay, so that means that they're cis. Okay, now these guys here, right, now with the cyclohexanes, you're going to want to check out what the axial and equatorial are. Okay, so for here, right, because on each carbon there's an up and a down. Okay, so for here, right, the axial, the carbon-carbon bonds point towards the axial. Okay, so that means that that means the axial is going up, which means equatorial, that this H is going down. Okay, same with this one here, right? The carbon-carbon bonds are pointed up, so that means the axial is up, which is this, which means there's a hydrogen that's pointing down. But since they're both the chlorines are pointed up, that means that this is cis. Okay. Now for here, right? So here the carbon-carbon bonds are pointed up, which means there's a hydrogen here that's axial that's pointing up, which means this is pointed down. And this here, right? This means that there is a carbon-carbon bonds are pointed down, which means there's an axial down. There's a hydrogen pointing down here. And since this is down, that means this is up. Okay? So we have an up and a down. It's trans. Okay? So be careful. In here, put in your hydrogens. Okay? For the cyclopentanes, not a big deal. But for the cyclohexanes, it's usually a good idea to go ahead and put in the hydrogen so you know which one's up and which one's down between the hydrogen and the group you're interested in. So then compare down, down, up, or up, up, right? Depending on what it is. Okay, so are the indicated carbon atoms chiral or non-chiral, right? So to be chiral, you need four different things. Okay, or distinct things. That's another way you can put it. Okay, so for this carbon here, right? So remember, there's 3 bonds shown, so there's a hydrogen here, right? That I don't have to show, right? So we have a CH3 here, right? Right. So for this carbon there, right? So there's a CH3 here. There's 2 bonds shown, which means there's 2 hydrogens, right? So, right. So that's a CH2. Here, right? There's 3 bonds shown, so there's a CH, right? So that's a CH. Okay. So we have an H, CH, CH2, CH3, all hanging off of that one carbon. So that means, right, this, and this, right? 4 different things hanging off of it, right? Just looking at the hydrogens. right? So that means it's chiral. Okay, so for this one here, again, I only have 3 bonds shown, so there's a hydrogen you have to see. So there's a CH3. Okay, so for this one here, it's a CH2, right? This one here is a CH. Okay, and again, you can look at H, CH3, CH, CH2, right? They're all different. Okay, so therefore, it's chiral. Okay. Now, if this was a CH2, this was a CH2, right? Right, with carbon, all the bonds are the same, right? We'd have to go here, and then see if those were the same. Okay. So for this one here, again, you have a hydrogen. I don't have to show, right? But it's there, right? So there, right? This is a CH2. This is a CH2. Okay. So this one has 2 carbon-carbon bonds, 2 carbon hydrogens, right? This guy here has 2 carbon-carbon, 2 carbon hydrogen, right? So it's a tie. So now we go down here, right? Again, I don't have to show those hydrogens, but they're there. So this one has 2 carbon-carbon, right? 1 carbon hydrogen, right? And 1 carbon oxygen. Same goes here, right? 2 carbon-carbon, 1 carbon hydrogen, right? Because I don't have to show that. 1 carbon oxygen, right? So it's tied. So we need to go here. Oh, we're to the same carbon, so obviously it's going to be the same. So that means this side of the molecule is exactly the same as this side of the molecule. So that means it's non-chiral. Or another way it says achiral. Okay, there you go. So if you don't see a difference from that first groups, right? Go one further out. That's the same. Go one further out until either of 1, 2 things happen. You either get to the end of your chain, and there's no differences, or like in here, or you find a difference, and then obviously it's chiral, or you get to inside your ring and you get to the same carbon, and there you go, stuff like that. So you've come to the same point. So that means that these sides are the same. Okay, so for R and S, okay. So for this one here, you're looking at priorities groups, right? So primarily you look at mass. That's the big thing. Technically it's molecular atomic number, but really mass is the better way of thinking about it. Okay, so you've got these groups here, right? So if it's the same, right? If you have a tie, you start looking at bonds, right? Which is the heaviest bonds. If there's still a tie there, you look at the number of those heaviest bonds. Okay. So for here you have you have a chlorine, hydrogen, carbon, carbon, right? So the heaviest thing is definitely going to be this chlorine here, right? The carbons are going to be next, but we don't know which ones, and then the hydrogens is definitely going to be the lowest. Okay, so for here, right, we have this one has 3 carbon-carbon bonds, 1 carbon hydrogen, right? Because there's only 3 bonds shown, so there must be a hydrogen hanging off of there. Here, there's 2 bonds shown, right? So it's 2, right? So that guy there has 2 carbon-carbon bonds, right? But there's 2 bonds shown, so that means there's 2 carbon-hydrogen bonds. Okay, so there we go. So, right, so there's still. The heaviest bond is still carbon-carbon, right? So that's a tie there. But this one has 3, this one has 2. So that means this has a higher priority than this one. Okay, so it ends up being 1, 4, 3, 2. Okay, so like that. So if you're doing the steering wheel method, right? So you need 4 in the back, which is great. That's exactly what you want. But since this is going clockwise, right, with 4 in the back, that means this one is R. Okay. Now, if you're using the hand method, right, your thumb would point towards where 4 is, which would be below the paper, right. Your hands would start over here at 1, sweep around to 2, which is over here, right, and then 3 over here. All keeping your thumb pointed towards 4. So 1 to 2, right. So 1 to 2. Okay. Since you're sweeping with your right hand, it's R. Okay. So this one here, right? So this one, right? There's a carbon, 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 right? So you're looking at those guys. Okay. So these 3 are definitely going to be higher priority than this one. So this one has to be 4. Okay, so when you look at the bonds, right? So this one here has one carbon-carbon bond, right? Two carbon hydrogens, right? Two bonds shown, so there must be two hydrogens, and one carbon chlorine. Okay, this guy there has two carbon-carbons, so therefore has two carbon hydrogens that aren't shown. This guy here is two carbon-carbon, two carbon hydrogens, right? So we look at the heaviest bond, so carbon-carbon, carbon-carbon, carbon-chlorine. Okay, so this one definitely has a higher priority than these two. So this is gonna be 1. Okay. Now, otherwise these two are a tie, right? So with that, so then we go out one further, right? So this one and this one, right? So this guy there, right, that has one carbon-carbon bond, 3 carbon hydrogens, right? So CH3. This guy here has 2 carbon-carbon and 2 carbon hydrogen, right? So heaviest bond is still carbon-carbon, okay, for here. So then we have to say that's a tie. But this one has 2 of them. This only has 1. So that makes this chain here a higher priority than that chain. So this ends up being 2. This ends up being 3. Okay, so if we rewrite this, 4, 3, 1, 2. Okay, so in this case, okay, you are with your thumb, right? Your thumb would be pointed out at you, and your fingers would sweep here to there, right? So 1 to 2 to 3, right? So you can just get 1 to 2, that's fine. So right, so you can always just turn your paper around, right? So 1 is over here, 2 is over here, 3 is back here, right? So 1 to 2 to 3, right? Your thumb's pointed up at you where the 4 is. Since you're sweeping with your right hand, it is that means that this thing is R. Okay. Now with the let me see if I can get a model kit here. So if you want to do the steering wheel method, right, you're going to have to rotate this 4 to the background. Okay, so 4 is coming at you, 3 is behind, 1 is over here, 2 is here. So if you're going to rotate this, you rotate that, right? So 4 is here, you can rotate this back. The 3 comes forward, 4 is going behind, but these two guys switch places, 1, 2, right? So going from here to there, right? They're switching sides, right? So now, okay, it's going clockwise with 4 going behind, so again, it's R. Okay, now this guy here, right? So you have a carbon attached, hydrogen, fluorine, bromine, right? So bromine's the heaviest, which is 1, right? Fluorine's next, which is 2. Carbon is the next heaviest, and then the hydrogen's the lightest. Okay, so you ended up like, so 1 is behind, 2, 4, 3. Okay, so now your thumb is going to be pointed. Thumb's going to be pointed this way. Okay, so that's where the 4 is. 1 is behind, 2 is up at you. 1 is behind, 2 is up at you, and 3 is over here. 3 is over here. Okay, so it's going to be like this. Okay, so with your thumb pointed this way, 1 is behind, 2 is this way, 3 is this way. Okay, so 1, 2, 3. Okay, so since I'm sweeping with my right hand, or excuse me, my left hand, it's S. Now, if you wanted to do the steering wheel method, right? So here, the 1 is the 1 is green, 2 is the 2 is red, 3 is white. So we would rotate it like this. Okay, so that, again, we got to put that 4 behind, but now the 3 is here, 2 is over here, 1 is there, right? Since you're going counterclockwise around with 4 going behind, that means it's S. Okay. Yeah. Next step is the atom a nucleophile or electrophile? Okay, so you are, right, so this is positive loving, right? So what things like positive charges? Things that have negative character to them. things that are negative loving, right? What loves negative charge? Positive charges. Okay, so all you got to do for this is to say, okay, look at these polar bonds here. Okay, so this bond here, right? So which is more electronegative? The oxygen's more electronegative, so that's going to be negative, positive. Right? Same goes with this one. This is positive. Electrons, the oxygen's more electronegative, so that's going to be negative, right? So like that. So this carbon here, right? It has positive character to it, so it's going to be an electrophile. This guy has negative charge, so it's going to be a nucleophile. Oops. Okay. So there we go. Same goes with here, right? So which is more electronegative, the carbon or the chlorine? The chlorine is more electronegative, right? So it's going to have negative, more electronegative. This is going to be positive character, right? So since it has negative character to it, it's going to be a nucleophile. There you go. And yes, the E's and N's are fine to write. I know what you're talking about. Yeah. Okay. Now I will give you this. I will give you what the reaction looks like. So it'd be A to B to C to D, right? Okay. So it has. So it'll look like. Oop, this is the product. So it'll just be D. Okay. So okay. So reaction has two intermediates. Okay. The second step of the reaction is slower. So this is slow. Of the first and third steps, okay, the overall reaction is not spontaneous, okay, so that means delta G 0 is greater than 0, okay, so with that, so non-spontaneous. So include the reactants, intermediates, products, transition states, delta G overall, delta G double dagger, which is your activation energy. Okay, so there we go. Okay, so you're going to start here, right, so I'm going to put the energy, reaction progress. I'll put these in. Okay, just start maybe about a third of the way up, and that'll be your reactants. Okay, so all the delta G's are relative to that reactant. Okay, so you're going across here, right? So and then up here, it's going to be delta G. So that just mark that somewhere up here. This will be delta G double dagger. Okay. Now, we know that there's going to be a couple intermediates. They're going to be, say, here and here. So those are the intermediates. Okay, there and there. Okay. Now, products. Okay. If it was spontaneous, it would be down here. But since it's non-spontaneous, it's here. Okay, so this is products. So that means the delta G double dagger is there, right? So delta G double dagger, which means, right, we're going up. It's greater than 0. It's going up. So that means it's non-spontaneous. Okay, now, right, so going from here to here, there's going to be a bump, right? There's going to be another bump and another bump, you know, from here to here. But which is going to be the high bump? The one that's slow. So this one here is the one that's going to touch the top, touch that line up there. All the other bumps are going to be below it. Okay, it's going to look like that. Okay, and these are your transition states. There, and there. Okay, so we have the reactants, we have the intermediates, we have the products. Okay, transition states, right? Here, here, and here. Right? Delta G there. Delta G 0. Delta G double dagger. Okay, we're good to go. Okay, so EOU. Okay, I'm going to give you this formula. I'm not going to give you the key, but I'm going to give you the formula on the equation sheet. Okay, so here we go. So this is 2 times the number of carbons, which is 6, plus 2. That's just a constant. Plus, there's no nitrogens. Minus the number of halides, right? My halides are the fluorines, chlorines, bromines, and iodines. Okay, so we have 2 of those minus 10 hydrogens. Okay, all divided by 2. So this is 1214 minus 12, right, over 2, right? So that ends up being, what, 2 over 2, which is 1. Okay, so for this one, right, so it means 2 times 5 plus 2, right, that constant, plus, there's 2 nitrogens here, right? Plus, there's, minus, no halides, okay, so 0, minus 8 hydrogens, right? All divided by 2. Okay, so it's 10, right? 10, 14, minus 8, all divided by 2. But notice in here in this equation, we did not have the oxygen. We just ignore it for this equation, okay? So like that. So right? So this ends up being 6/2, which ends up being 3. There we go. That's it. Just got to know how the, right? So if you're getting a half number here, right, you can't have 3.5 degrees of unsaturation. It's just a whole number, okay? So it has to be some sort of whole number, integer. So like that. So, okay. Okay. Okay, so alkenes, alkynes. Okay, so now you're gonna have to put cis and trans in with just the alkenes. Okay, you don't have to worry about the alkynes, right? There's no cis and trans in the alkynes. Just the cis, just these. Okay, so here we go. Put in your dots. Okay, so you do the main chain, right? So with that, it has to include this double bond here, right? So you can go 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, 6. Oh, well, that works. 1, 2, 3, 4, 5, 6. Okay, well, it doesn't really matter. We'll do this one just because. Okay, so here we go. So, right, so main chain is 1, 2, 3, 4, 5, 6. So C6, which would normally be hexane, right? It's our base, right? But since we have a double bond, we're going to say that's hexene. Okay, now we're going to need to figure out, right, so where that alkene starts, okay, for when we do our numbering. But then we also have this ethyl group here. Okay. Now for here, the numbering, for carbon 1 is the one that starts the end that's closest to the double bond. Okay, so it ends up being here. So it's 1, 2, 3, 4, 5, 6. Okay, so with that, so the alkene starts at 2, right? The ethyl ends up at 4, right? So with that, so it ends up being 4 ethyl, 2 hexene. Okay, but we have to include the cis and trans here, right? So the way to do this is to look to see where those hydrogens are. Okay, notice how they're both on the same side. That makes this cis. So it ends up being cis 4 ethyl 2 hexene. Okay, now for this one here, again, you're going to put in. You can put in your dots. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Right? Okay. So this is going to be our main chain, right? The main chain has to include that triple bond in there, right? So C8, right? Which would be octane. Normally be octane, right? But since there's a triple bond, it's octyne. Okay. Now with the numbering, right? 1, 2, 3, 4, 5, 6, 7, 8. Right? So with that, so okay, so we have this, right? So we're gonna have to say where that alkyne starts, right? We have this methyl group. Okay, we have a propyl group, right? Because there's 3 carbons, right? So propyl. But then again, since it's going connected to the main chain through carbon 2, it's a 2-propyl group, or an isopropyl, either way. Okay, so the alkyne starts at carbon 1. Okay, the methyl's at 4, right? The 2-propyl group is connected to carbon 5, right? So methyl comes before propyl, right? So it becomes a 4-methyl, 5 2-propyl, 1 octyne. There we go. There you go. Okay, now for E and Z, right? You're going to need to split these guys through the carbons. Okay, you're going to see what's happening on this carbon, what's happening on this carbon. Okay, so you got to split it like this. Okay, we're going to use the same priority rules as the R and S. Okay, so for here, right, it's chlorine versus nitrogen, right? So chlorine's heavier, so this has a higher priority, high, low. Okay, now for this guy here, right? Okay, so this, right? So that they're both carbons, right? So it has 2 carbon-carbon, 2 carbon-hydrogen, right? This guy there has 2 carbon-carbon, right? 2 carbon-hydrogen, right? I know you could probably do this on your own, but it's a good practice. Just go ahead and just do the go through the same process each time. Okay, so that's a tie. So we're going to go one further out, right? So we're going to look at this guy here, right? So that one, 2 carbon-carbon bond, 2 carbon hydrogens, right? But this guy here only has 1 carbon-carbon bond and 3 carbon hydrogens, right? So since this only has 1 carbon-carbon bond, this has 2, right? Because that's the heaviest, right? That means this is high, this is low. Okay, so you look to see where the highs are. Highs are both up, right? So that means, they're on the same side, right? So it's Z. Okay, do your best bad German accent. Okay, so for this one, okay, again, we're going to split it down there, right? So hydrogen versus carbon, right? So that means this is the high, this is the low. Okay, here, right? So we have, right? We have 1 carbon-carbon bond, 3 carbon hydrogens, right? That guy there, right? That has 2 carbon-carbon, right? 1, 2 carbon hydrogens, right? So they're both carbon-carbon, right? That's the heaviest bond, but this one has 2 of them. So that means this ends up being the high, this ends up being low. Since they're on opposite sides, it ends up being, the highs are on opposite sides, they end up being E. This is the E configuration. Okay, there you go. Okay, so there will be a mechanism. Okay, so you're either going to have adding bromines. Bromines and chlorines, they work the exact same way. It's just adding chlorines with adding bromines, okay? With or without the presence of water, okay? So if you're going to do this, right, so if you have something like this, okay, the way this works, right, so bromine, bromine, right? So this is going to attack here, push that away, to make this. Oh, I'm going to tell you what the structure is. Okay, so bromine goes there, H plus goes there. It doesn't technically matter. This is probably a better way of doing it. But the important thing is that one of these, well, right, so plus would be our minus. Okay, one of these lone pairs is going to make a bond with, is going to be attracted to that positive charge there, and so you're going to get this nice resonance structure of the bromonium ion. Okay, so it could stabilize itself while it's waiting for this bromine to attack. Okay, and now eventually the bromine's going to get off its butt and then go there. Okay, to make that. Okay. Now, if you're going to do this with, let's say that there was water in there. Okay, I'll go back here. So let's say you do the exact same reaction, but instead I had water around, right? You'd end up with this product, right? So you know, eventually the water's going to have to attack, right? Because the right, because you need an OH here, right? But again, the first step is exactly the same, right? This comes in, attacks there, pushes that guy away to form this. Oop. Right, notice the bromine's there, right? So bromine's going to go there, right? This has lone pairs on it, right? So plus Br minus. Okay, but again, you're going to have this bromonium ion, which kind of comes in here. Like that, a nice transition state. But instead of having this attack, what's actually going to happen is the lone pairs on the water, when these lone pairs, the water is going to attack, okay, to give you this. Right? I'm going to just draw it up here because it's make it a little easier to see. Okay, so one of these lone pairs has made a new bond with that carbon. Okay, but unfortunately it has the positive charge, right? So HBr. Okay, so that means this bromine is going to come in, grab that hydrogen, push that away, and end up with that. Okay, so first half of this reaction is going to be exactly the same. It's just, does the bromide come in and attack? You'll know that because there's be a bromide here. Or does water come in and attack? If that, then you get the chlorohydrin or the bromohydrin, right? Because you have an OH attack. But they're exact same reaction or mechanism. Okay, design a synthesis. Okay, so for these, okay, the thing to do, the place to start with is to say, okay, how do I get this functional group here? Notice how this is, right? So it's a cis double bond. Okay, so what puts in a cis double bond? Well, it's H2 Lindlar. Okay, just in general, that's how we put these in. Now, what does if we're going to do that reaction, what does the molecule have to look like? It has to look like this. Okay. Now we're all set up. Okay, we have all the carbons in place to be able to do that last chemistry, put that functional group in. So now let's start building this. So up to this point, you didn't even have to worry about that. Okay, but notice how this looks amazingly like this. Okay, and then all we have to do is add an extra carbon, right? Extra carbon. Okay, so we probably should start with that. Okay, we're going to have to rip off that hydrogen, right? So sodium, so you add sodium amide, that'll rip that away. You make yourself a nice carbon nucleophile. Okay, now all we need to do, right? So we have 3 carbons, right? We need 3 carbons, 1, 2, 3. All we have to do is add a CH3 group, which all we have to do is use this guy there. We dump that thing in, right? This is going to attack, push that away to make this molecule here, right? Which then you can do the H2 Lindlar. So here's your synthesis, right there. Okay, but the way we did this is still the same, right? So we figure out what the last step is going to be, right? We're going to put in that functional group. It's going to be, in this case, H2 Lindlar, right? Well, what does the molecule have to look like in order for us to do that? It has to look like this. Now we start to build this. Okay, so this part here comes from there. Right, but we just have to add an extra carbon, right? So an extra methyl group here. If it was, I don't know, 4 carbons long, right? We have to pick this. You know, we have to have 4 extra carbons, right? We'd have to add this guy, right? So with that, so there you go. But the process is the same. Okay. Okay. Now for this one, okay. Now there's a couple of different ways you can solve this, okay. But one of the best things to do, right, is to say, okay, how do we put in, right, so we have to use these carbons here, right? Always a good check to say, how many carbons do we have? 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. Okay, so we have 6 carbons here, 6 carbons, right? 6 carbons here, 6 carbons here. So we don't have to worry about any ozone clipping it off, anything else like that. Okay, so we're good with that. That's always a halfway good check to look at. Okay, so we're adding an oxygen on, you know, for here, right, this would be secondary, this is secondary, right, but this one's the primary. Okay, so compared to here, there wouldn't be any, right? So we know some reactions that had hydrogens or oxygens, right, where we can get some specificity. But this one, if you think about it, is on compared to these two, right? This is secondary, this one's primary. So add oxygen on the less substituted side, right? And you can certainly see that with this one here, right? So if we add here, we're gonna have to activate that carbon there. But if we're just looking at these two here, right? These are already sort of activated, so you can do some nice chemistry here, right? So we're looking at just those two, right? What we're actually doing is we're adding an oxygen on that side, right? Which is the more substituted side. So how do we do that? We usually use the those mercury salts. H2O, H+, that sort of stuff. Okay, we usually use the mercury reaction, right? And there's a nice way to put in a ketone if we start with that. Okay, so remember we put an OH on this side, which then orthotomerized to that. Okay, so now the question becomes, how do we build this? How do we take this to this? Well, how do we make a triple bond? Right? We actually just do it by making 2 double bonds, right? So with that, so right in base, oops, right, remember there's hydrogens here, right? So the first one, rip this off, that collapse down, kick this away, more base, grab one of these, collapse down, kick that off to make this. Okay, so how do we put bromines across this guy? Pretty simple. You just add bromine. It'll add it right there. So here's your synthesis. Okay, there you go. But the process was still the same. Is to say, okay, take a look at this, to say how do we put in these functional groups, right? Well, we have 6 carbons and 6 carbons, so ketone, so a slicing reaction like ozone probably isn't going to be warranted. Okay, so but notice how these two are activated here already. We can go ahead, right? So if we think about these two, right, this is primary, that's secondary. We know how to put an oxygen group on a secondary carbon versus a primary. We have to do that using the oxymercuration, right? So, but in order for that to do that, you can do that. Okay, there's a couple other ways that you could do it too, but this is a halfway decent one. As long as it's valid, you're fine. So, but you know, once you get to here, then you can sort of see how do I go from a triple bond or a double bond to a triple bond. Well, we go here to there. Here we go. Okay, name the following compounds, right? So with that, so this is the for halides, right? So halides don't get any other priority compared to like methyl groups or anything else like that. So they're just there's nothing special about them. Okay, so we're gonna look at this, right? So put in your dots. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it doesn't really matter. So we'll just take out of habit. I'll take the so C9, take the horizontal. So nonane, okay, right? And then we have, right? So then we have this guy here. So we have an ethyl group. Okay? We have bromine, which would be a bromo, right? And then we have that methyl. Okay, so if we do from this side, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So that means the ethyl group's at 3, the bromo's at 5, the methyl group's at 6, right? If we go from here, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So that means this methyl group's at 4, it's at 5, that's at 7, so we're going to add these up, so that's 9, so it's 14, this is 11, this is 16, so here's the lower numbers. Okay, so which comes first? Well, it turns out the bromo comes first alphabetically, so it becomes 4 bromo. Right? Ethyl comes next, so that's 3 ethyl. Right? Methyl's last, right? 6 methyl. Nonane. Okay. Okay. Now for this one, again, you got to put in your dots for your carbons, right? Okay, so here the longest, right? So here's a 3-carbon chain, 1-carbon chain, but we have a 6-carbon ring here. Okay, so C6, hexane, cyclohexane. Okay, so we've got this again. We have a 2-propyl group here, right? It's propyl, right? Because it's 3 long. It's connecting through the carbon 2, so it's a 2-propyl group. Right? We have a methyl. We have that chlorine or chloro group here, right? Okay, so if we want to say start here, right? So 1, right? So the nearest side chain neighbor is here, so we're going to go clockwise. 2, 3, 4, 5, 6, right? So it becomes 1, 3, 4, right? So if we wanted to say this was 1, right? So nearest side chain neighbor is here, so 2, 3, 4, 5, 6, right? So this would be 1, 2, 5, right? Now if we wanted to do this one as 1, so it'll be 1, the nearest side chain neighbor is here, so now we go counterclockwise, so 2, 3, 4, 5, 6, right? So it becomes 1, 2, 4, right? So you add them up, so this becomes 8, 8, 7. Okay, so this ends up being the numbers, these are the numbers we use, okay? So chloro, right? Chloro comes before methyl, which comes before propyl. So it becomes 1 chloro, 2 methyl, 4 2-propyl, cyclohexane. There we go. Okay. So with that, so for this one here, right, so for the monosaccharides, right, so I'm going to give you this portion here, right, just like on the last test. Okay, so you need to know two things, right? You need to know, aldehyde versus ketone, right? And you need to know number of carbons. Okay, so here we go. So this one here, here's where the acetyl bond O is, right? There's carbons on either side, right? So that means this is a ketone. So we're going to say this is a keto sugar, and then there's 1, 2, 3, 4, 5, 6, 7, right? So don't forget that one there. So 7 carbon sugar, heptose. So it's a ketoheptose. Like that. Okay. Now this one here, right? So notice it has a double bond O with an H on one side, so that means it's an aldehyde, which means it's an aldo. Okay. And then there's 1, 2, 3, 4, 5, 6, right? Don't count that hydrogen. We're just counting carbons. So there's 6. You come over here, 6 hexose. So it's an aldo hexose. There you go. Okay, now for DNL sugars, right? So for the straight chain, all you care about is this one here, right? So for this, right, so this one here, it's pointed that way, which makes it a D. Okay. Same thing with this one here. Notice how this one here doesn't matter about any of the other ones. It's just that one here. That one's pointed that way, which makes it an L. Okay. Now for this one here, what you're looking for is this CH2 group. Okay. If it's above the ring, right, which it is here, that makes it a D. If that CH2 group is below that ring, that means it makes it an L. So this is D, D, L. That's it. You just have to know what you're looking for. Okay. The things that are important. This, straight chain is the carbon. It's technically the chiral carbon farthest away from the aldehyde. So it's here. Okay. So usually one up. Right, up. Okay. If it's pointed that way, it's D. If it's pointed that way, it's L. On a ring here, it's the CH2 group, right? So if it's above the ring, it's a D. If it's down here, if it's been down here, it is it's L. There you go. Okay, linkages. Now for here, right? So with that, so you're going to look at each linkage in isolation. Okay. So you look at that. Look at that. Those two sugars, right? Those two sugars. Okay. First thing to do is to take a look at the ring. Get the numbering down, right? So you can mark your carbons, right? Don't forget this one. Don't forget that one. Okay. Okay, now, I'm only going to give you aldoses. Ketoses become a real pain in the butt. So I'm just going to give you aldoses. Okay, so if this is a 6-membered ring, right? So there's 1, 2, 3, 4, 5, 6. 6-membered ring. Okay, that means carbon 6 is going to be the one on the outside. If it was a 4-membered ring, that would mean carbon 4 would be out. If it was a 5-membered ring, that would mean carbon 5 would be out. And now just going to go backwards, right? Counting carbons. So 1, 6, 5, 4, 3, 2, 1. Okay, for here, again, 6, 5, 4, because it's a 6-membered ring. 3, 2, 1. Now, if you get here and you're at either, if you stop 1 here, something's happened. If you get here and you're at 2, something's happened. Okay? You're just counting carbons, right? So 6, 5, 4, 3, 2, 1, and then 6, 5, 4, 3, 2, 1. Okay, so now we're just looking at this one, right? So we're taking a look at the left-hand sugar, right? So you have to remember, alpha's down, beta is up. Okay? So for here, just for this sugar, right? This is the left, this is the right. Okay, so since it's going down, okay, relative to the left-hand sugar, right? So that linkage is going down, that means it's alpha, okay? And it's going from carbon 1 and then go left to right, carbon 1 to carbon 6. So it's alpha 1, 6. Okay, now for this linkage, right, we're only interested in these two sugars, right? So now this is the left-hand sugar, this is the right-hand sugar. So this bond is going up relative to the left-hand sugar, which is this one. Okay, that makes it beta. And it's going from carbon 1 to carbon 4. Okay. Now for this one here, again, you're going to look at it in isolation. Okay. Now this one is the left-hand sugar. Notice you would think, oh, you just follow this chain around. No, here there's a reason why it's written like this. This is the left-hand sugar. Okay, so now this relative to that is going down, so it's alpha. So it's going from carbon 2 to carbon 6. So it's an alpha 2,6. Okay. There you go. Good luck.